Today I'll be teaching the base catalyzed aldol reaction. So by the end of the video, you should be able to know what the starting materials are, what the mechanism is for base catalyzed aldol reaction, and the products that are formed. The aldol reaction is a coupling reaction, which is just a formation of a carbon-carbon bond. So the starting material for today is going to be ethanol. So to start an aldol reaction, we have to remove an alpha hydrogen from an alpha carbon. So the alpha hydrogen is going to be in green. And to tell if something's an alpha carbon, it's always a carbon that's connected directly after a carbonyl right over here. In order to remove the alpha hydrogen, we're going to be using a strong base. So the base I'm going to be using today is hydroxide. So the hydroxide is going to attack the hydrogen and it's going to form a water molecule. And then the electrons from the carbon-hydrogen bond is going to go to the carbon, making it a carbanion. This carbanion has a resonance structure called an alloy, which is where the negative charges move to oxygen and then the bond forms on the carbon. So today I'll just be using this example over here. So the carbanion is going to attack the carbon that's connected to the oxygen. So the reason it's going to be attacking this carbon specifically is because this carbon has a slightly positive charge due to the polarity of the oxygen. So once the carbanion attacks the carbon over here, this is the formation of our carbon-carbon bond, which is seen right over here. And now this oxygen over here becomes negatively charged. So this oxygen is going to attack the water molecule that we formed earlier to protonate itself. So the electrons are going to attack the hydrogen from this water molecule and then move the electrons back to this oxygen right over here. And then we made our product aldol. The aldol molecule that we just formed can go through an additional reaction where the carbon-carbon bond that we just made right over here can become a double bond. So in order for this to happen, we're going to have to be in a basic solution with heat. So we're going to be using hydroxide as our base again. So the hydroxide is going to attack the hydrogen again, forming another water molecule. And then the electrons from this carbon-hydrogen bond is going to move right over here between the carbon present in the alpha carbon and then the carbon connected to the oxygen. And this is going to result in a double bond. And then the electrons from the double bond between carbon and oxygen is going to move to this oxygen right over here. So this is going to be our intermediate product. So with this intermediate, we're going to have one of the lone pairs from the oxygen come back and form a double bond between the carbon and oxygen. And now the double bond that we had present right over here is going to go and be moved to the coupling carbon bonds that we made earlier, and it'll be kicking off this OH group, and this will be our final product. An aldol reaction can lead to 4 possible products depending on the starting materials you use. So in this example, we're going to have ethanol and acetone present in a solution. So there are 4 possible products that can be formed. So one possible product is ethanol reacting with ethanol, acetone reacting with itself, and then a combination of ethanol and acetone reacting with each other. So the reason both of these molecules can be used in an aldol reaction is that they both have alpha carbons present. Ethanol only has 1 alpha carbon present right over here, while acetone has 2 alpha carbons present, so it has multiple alpha hydrogens to remove. One of the first products that can form is an aldol reaction occurring between acetone and acetone. So the product that would form would be this. The reason you can tell this is between the acetone and acetone is by the number of carbons present. So as you can see, this product has 6 carbons present. So if you think about it, an aldol reaction requires 2 molecules. So if you do 6 divided by 2, that means that the predecessor had to be acetone in order for the number of carbons to add up. So the second self product is going to be a combination between ethanol. So the reason you can tell is between ethanol is by the number of carbons. This molecule has 4 carbons present. And the only way to have 4 carbons present in this molecule if both starting materials had 2 carbons present. And this will have to be with the ethanol. So the final 2 products that can form are a mixture between ethanol and acetone. So depending on what alpha carbon is deprotonated will determine which carbonyl will be acting as the nucleophile and which one will be acting as the electrophile. So as you can see, the final 2 products are right over here. So with the first mixed product, you can tell that the acetone had the alpha carbon deprotonated. The way you can tell is by which carbon-oxygen bond formed an alcohol, and by the coupling of the carbons as well. So as you can see, the coupling occurred between carbon 3 and 4. So if you were to erase this bond, you have to imagine what this attachment would have been without it. And the only starting material that has 2 carbons will have to be ethanol. So if we look at the last mixture product, we have to see what alpha carbon had its alpha hydrogen removed. So if we look at where the coupling would occur, it would occur between 2 and 3. So if you were to remove that bond, you can tell that this part of the molecule will have 3 carbons, and then the left side of the molecule will only have 2 carbons. So this indicates that the ethanol had its alpha hydrogen deprotonated and then attacked the acetone, forming the coupling bond between the 2 carbons, making this final product. So I'll now be going over some additional practice problems. So in this question, we're going to have acetone reacted with benzaldehyde. As you can see, both molecules have an alpha carbon, but the acetone is different from the benzaldehyde. The acetone has alpha hydrogens present right over here, but the benzaldehyde doesn't have any alpha hydrogens present at the alpha carbon. So this indicates that the acetone is going to have its alpha hydrogen deprotonated, and then the carbonyl anion that would form is going to attack the benzaldehyde, making this product right over here. So I will now be doing a practice problem that involves intermolecular forces. As you can see, we have this symmetrical molecule right over here, and it's going to be going through an Aldol reaction. So initially, you can see that this molecule has 2 alpha carbons present, one located at carbon 1 and one located at carbon 3. So we have to determine which alpha hydrogen is going to be deprotonated. So we have to think about the stability of it. Since we're going to be doing an intermolecular force, we're going to be forming a ring, a cyclic ring. So we have to determine what number of carbons will form the best cyclic ring. So if we were to do it right from carbon 3, we'll have a cyclic ring that has a carbon number of 1, 2, 3, 4, which isn't stable. So if we did it from carbon 1, we'll end up having a cyclic ring that is 6 carbons long, which is very stable. So if we go over the mechanism, we're just going to have the hydroxide deprotonate the alpha hydrogen and then making the carbon 1 a carbonyl anion. So now this carbonyl anion is going to be attacking the other ketone, which is going to result in this cyclic ring right over here. So similar to the mechanism earlier, the water molecule that is formed is going to be deprotonated, and it's going to protonate this oxygen right over here, and then we're going to end up with our final product right over here. I will now be going over some synthesis-based questions. Our first synthesis molecule is going to be this compound right over here. So from what we learned today, we know that if we have a ketone present next to an alkene, that there had to be an alcohol present between this carbon, and there had to be an alpha hydrogen that was removed from this carbon. So that means this was our product before hydroxide and heat was added.
Whenever we see a ketone and an alcohol separated by a carbon right over here, that means that a coupling reaction occurred. So if we were to imagine if this carbon bond right over here was removed, that our starting materials will involve an ethanol right over here, and then this molecule right over here up to this point, which would be these 2 molecules. So now if we were to do our synthesis, the starting material will have to be this one right over here. The reason it has to be this starting molecule is because if we were to remove the alpha hydrogens, it will attack this carbon right over here, which will eventually lead to this molecule, which will lead to the final molecule that we want. So if we were to have this as our starting material, we're going to need a strong base, so I will be using hydroxide for my synthesis, and then it'll result to this carbon with the carbonyl anion, and then I have it where we're going to have the ethanol right over here as part 1, and then part 2 is going to be the hydroxide and heat, and then we'll have our final product right over here. We're doing one more synthesis-based question. So as we can see, we have this material right over here, and we're trying to make it. So we see that we have a ketone and alcohol functional group, which means that we had an Aldol reaction occur. So we have to locate the alpha carbon, which is right over here, and we have to see where it connects to. So we connected to this carbon right over here. So we have to imagine that this carbon-carbon bond right here did not exist. So what would our starting material on the right be? And it would just be an acetone. And then our starting material, other starting material would just be this one without the carbon-carbon bond attached to it. So it would be this. And we know that this material will have to be attacking the acetone based on the alcohol that was formed. So this is going to be our initial step. We're going to have this starting material be deprotonated by a hydroxide group, and then we're going to have it form a carboanion. And then all that we need is just the acetone to make our final product. So today I went over the starting material, mechanism, and synthesis of a base catalyzed Aldol reaction. I additionally went over what alpha hydrogen is, an Aldol reaction involving intermolecular forces, and the and reactions that involve alpha carbons without alpha hydrogen present.